This video will see how do we get linear equations using Excel. So in my last video, the linear functions video, I showed this a little bit on the last two problems. But Excel is a wonderful tool in the sense that if you give it data, it can come up with a linear equation for the data. And today specifically, we're looking at examples of linear regression or finding linear trend lines. So this is a situation where we are given data points and we're trying to find the line of best fit or the best fit model that models the data so that then we can use that equation to make predictions and other inferences about our set of data. So let's look at two examples. Anthropologists use a linear model that relates femur height or femur length to height. The model allows an anthropologist to determine the height of an individual when only a partial skeleton, including the femur, is found. In this problem, we find the model by analyzing the data on femur length and height for the 10 males given in the table. And if I were you, I would take a second and type in the data in the table. I'm going to scroll down so you can see all of it. Got a little excited there. There we go. So that you can follow along with the video in Excel. So first thing we want is what is the linear model that shows the relationship between the femur length F and the height H. So to find our linear model, we're going to start by inserting a scatter plot. We'll highlight all of our data, then insert a scatter plot, and you want to pick the very first one with just dots, no lines. And then I'm going to change my quick layout to the first one so that we have a place to title and label our graph. So our input is the femur length, my T there, and then our output is the height of the person. So we're saying that their height is related to how long their femur is. So we are predicting the height. And we can see that these dots are kind of all over the place. If you squint, they look kind of like a straight line, but they're not exactly straight. So Excel is going to come up with the best equation that goes through as many of the dots and gets as close to the rest as possible. So to get our linear regression line, we right-click on one of the points and then add trend line. Then we want to check the box for linear and then check the boxes to display the equation and display R squared. And this gives us our prediction. So let's see. I don't have much room on my screen here. Let's just talk about this equation right quick. So we see that our slope is 1.92. This tells us for every centimeter our femur increases in length, our height is increasing by 1.92 centimeters also. So every time our femur increases by 1.9 centimeters, every time our femur increases by a centimeter, our height increases by 1.9 centimeters. And then the initial height is 80, saying that if our femur was 0 centimeters long, our initial height would be 80, which I don't know if that really makes sense. I guess that's saying if someone doesn't have any legs, that'd be 80 centimeters. Sometimes the initial value doesn't make complete sense in the problem. But the big thing is the slope, saying that every time our femur increases by a centimeter, our height increases by 1.92 centimeters. So I'm going to try to scooch this graph a little bit out of the way. We don't need it now that we have our equation. So we just retype this equation so that we have it to work with. So we're saying that our height is equal to 1.92 times our femur length plus, what is that number? 80.68. And that's our equation that we're going to work with. So an anthropologist finds a femur length of 58 centimeters. How tall is the person? So the femur length was 58. We're going to put that in for F. We say 1.92 times 58 centimeters in the femur plus 80.68 tells us that this person was 192.04 centimeters tall. And the next one, if a person is 151 centimeters tall, what does the model predict for their femur length? Well, now we know our height, so that goes in for H. So 151 is equal to 1.92 F plus 80.68. We're going to need to do some math, so we need to subtract 80.68 from both sides. I'm not going to do this one in my head. I'll actually do it in Excel. So we subtract 80.68 from both sides to get that 70.32 is equal to 1.92 F. And then to get F all by itself, to get the answer, we need to take 70.32 and divide it by 1.92. So if somebody is 151 centimeters tall, we predict that their femur length is 36.63 centimeters, rounding that to 2 decimal places. All right, next example. A convenience store manager notices that sales of soft drinks are higher on hotter days, so he assembles the data in the table. What is the linear regression equation that shows the relationship between the number of cans sold C and the high temperature T? So again, here's our data. You might want to pause the video and type this into Excel so you can follow along. So to get our linear equation, we start by highlighting all of the data, then inserting a scatter plot. I'm going to change my layout to layout 1 so that I can type in axis labels. We've got our high temperature, we have cells, and this is just temp versus cells. I don't really care what you title and label your graphs with as long as you put something there. So then to get our linear equation, we right click on one of the dots, add trend line. We want linear, display equation, display r squared, and close it. So our linear equation is 16.14 minus x minus 621.83. So what this is telling us is that if the temperature was 0 degrees outside, we would sell negative 621 drinks. That's our initial value. That doesn't really make sense. I think I said on the last one, sometimes the initial value doesn't really make sense in context, and that's okay. But the big thing is for every temperature or every degree the temperature increases, we will sell 16.4 more drinks. So our slope is telling us that we sell 16.4 more drinks every time it gets 1 degree hotter. And in theory, if it was 0 degrees outside, we would sell negative 621 drinks, but that doesn't make sense at all in context. So let's just take a second and talk about this r squared value. So r squared is a measure of how well does the line fit the data. The closer r squared is to 1, the better the fit. So in this case, since our r squared is 0.935, that's pretty good. And you can see that the line goes through and is really close to most of the data. So we would say this is a pretty good regression. On the previous one, let me bring my graph back because we didn't talk about it. This r squared is a little bit lower at 0.932, but it's still a good fit. It's still really close to the data. So r squared, again, is a measure of how well does the line fit the data. The closer it is to 1, the better the model that we have. Okay, so we have our equation now. Let's write it in terms of our variables. Sorry, I know it's kind of flashing around the screen. So let's see, the cans sold is C. That's going to be equal to 16.42 times the temperature minus, what was that number? 621.83. So that's our linear equation. So it says predict the cells if the temperature is 95 degrees Fahrenheit. So I'm going to put 95 in for T, since that represents our temperature. So 16.42 times 95 minus 621.83 tells us that we would sell 773.87 cans of soda if it's 95 degrees outside. And again, please leave your answer to 2 decimal places. Do not round to the nearest can. I want to see everything to the precise answer so that I know you did the math correctly. And this next one says, what does the model predict for the temperature if the number of cans sold was only 95? So this is telling us we sold 95 cans. That goes in place of C. 95 is equal to 16.42 T minus 621.83. We need to, we need to add 621.83 to both sides. We typically subtract because we're typically adding, but in this case, we're subtracting already, so the inverse of subtraction is addition. So we need to add 621.83 to both sides. So we would get 716.83 is equal to 16.42 T. So then to get T all by itself, we take 716.83 divided by 16.42 to get that T is equal to 43.66. So if it was 43.66 degrees outside, we would sell 95 cans of soda.